Hello, welcome. We're so excited that you guys wanted to come out and do some math this evening. It's a good day for some math. So it's my pleasure to introduce Dr. Eugenia Cheng, our speaker. She got her PhD at the University of Cambridge in pure mathematics. She taught there, but she's also taught at the University of Chicago and the University of Nice and the University of Sheffield. Right now, she's a scientist in residence at the Art Institute of Chicago. You'll have to ask her about that afterwards. In addition, she's a pioneer of math on the internet, and especially math on YouTube. She has her videos there have been watched, viewed over 1 million times. Today she's going to talk about ideas from her book, How to Bake Pie, which has garnered widespread attention from the New York Times, National Geographic, Scientific American. In addition, this month, she has a new book coming out, Beyond Infinity, so you should look for that. And apparently that doesn't keep her busy enough, so she's also a concert pianist. So please help me in welcoming Dr. Eugenia Cheng.
Thank you. Well, thank you, Karen, for inviting me, and thank you to the Newhouse Center for hosting my visit. And thank you all for coming to hear about math and food. And the reason that I wrote this book about math and food is that I love food and I love math. And unfortunately, most people love food more than they love math. And this makes me sad. And so I decided to try and bring my love of food and just edge it over to try and show everybody in the world that math is also lovable in the same way that food is, and that it doesn't have to be like that boring thing in school when you have classes and you have tests and you have loads of things to memorize. That's not really math. And so if people don't like that, I completely sympathize, because I didn't like that either. Whereas food and cooking can be much more interesting if you make things up for yourself. And also, some people don't like following recipes and weighing things out very precisely. And the time it gets really interesting is where you just go into the kitchen by yourself and experiment, make up recipes, and just decide whether or not you think it's delicious. And that's what math is more like when you get to a research level. And I think it's a shame that most people don't get to see that unless they get to a research level. And of course, most people in the world don't go on to do research in mathematics. And I'm not suggesting that everybody should or could go and do research in mathematics. I just think it's possible to appreciate that aspect of math without having to jump through all the hoops and pass all the tests and memorize all the formulae that we tend to get people to do. So I decided to subvert the system and just show everyone my favorite parts of math without having to pass all those tests. And the thing is that when I was young, I was very lucky because I have a mathematical mother who showed me some of the most interesting and cool parts of mathematics that I would never have seen otherwise. And this led me to know somehow that there was always a more beautiful part of math waiting for me if I could just get through all those equations and formulae and things. And I know most people don't have a mathematical parent who's showing them the cool stuff. And that's why, one of the reasons why I wrote this book, to show people the cool stuff that might, as it were, inoculate you against boring math classes in middle school so that you still continue to believe that there's something great out there. Of course, my ultimate aim is to change the entire education system so that there's less emphasis on tests, less emphasis on standards, and also so that teachers can be allowed to teach the things that they truly believe in. Instead of having standards and methods and curriculum imposed on them that they have to try and achieve, rather than what I think is better, which is trusting good teachers to share the love of the thing that they want to share in the way that they see fit. So I am going to show you what I love the most about math. I'm going to show you some of my favorite mathematical structures. And this includes Bach, juggling, hair, factors of 30, that's more obviously mathematical, cake, and custard. Now, you may not think that these things are obviously mathematical, but I think that math is everywhere. And so I'm going to make good on that belief and show you how math is in all of these things, perhaps in ways you weren't expecting. So first, I need to tell you what math is really. Because one of the most common myths about mathematics is that it's all about numbers, or that it's all about right and wrong, or that it's all about solving equations. And although math does include those things, it's definitely not limited to those things. And in fact, the math I do is category theory, and it has no numbers in it whatsoever, and it doesn't really have any equations either. So what is mathematics? I think that mathematics is the study of how things work. But it's not the study of how any old things work. It's the study of how logical things work. And it's not any old study of how logical things work. It's the logical study of how logical things work. And this is why I think it's relevant to everything, because, and to everyone, whether you work in an obviously mathematical field or not, because everything has some logical aspect to it, some more than others. Wouldn't it be better if everybody thought more logically, especially in the world at the moment? So the trouble with this as a way of studying things is that actually nothing really does behave logically. I don't behave logically, not really. Even Karen doesn't always behave logically. This computer definitely doesn't behave logically. So in order to study anything logically, we have to ignore the pesky details that stop things from behaving logically. And when we do that, we forget some details, and that moves us from the real world into the abstract world of ideas, which is where everything does behave logically. And that's a beautiful world where you don't have things like when you try and teach a small child how to add cookies up, and you say, if I gave you one cookie and another cookie, how many cookies do you have? And they go, none, because I'll eat them all. And then you say, OK, well, you're not allowed to eat the cookies. And then no wonder they think that math is kind of boring. Oh, what's the point of cookies if I'm not allowed to eat them? So in the abstract world, everything works according to logic. And this move from the real world to the abstract world is one thing that can make people feel afraid. And I understand why, because once you've done that move, you don't really have your feet on the ground anymore. You're floating around in the air somewhere. The benefit is that everything works according to logic. Now, some people like winning arguments by yelling. And if you like winning arguments by yelling, then you don't like the abstract world, because you can't win arguments by yelling in the abstract world. In the abstract world, you can only win arguments by proving things logically and justifying them logically. And if you like things that work logically, then this is a good place. In a way, I'm just like that small child who doesn't stop asking why. You know, they say, oh, why does this happen? And you give an answer, and they go, well, why does that happen? You give an answer, and they go, why? And then they give an answer, and they go, why? Maybe they do it just to annoy the adults. I sometimes like annoying adults as well. But for me, the answers to the why questions never satisfy me until they become mathematical. Because otherwise, there's always some other why question that I can ask, and it becomes mathematical. And my journey into mathematics went like this. When I was in high school, I wished I could just be studying science. I'm interested in everything else. But in terms of actually rigorously studying, I just felt like science was a better place to be rigorous for me. And then in the UK, which is where I grew up, when you're 16, you get to specialize into just a few subjects. And so then I just did math and science, and it was great. But then I thought, if only I was just doing math. And then I got to university, and you get to just study one subject in Cambridge. So I just did math, and I thought, if only I was just doing pure math. And then in my final year, I was just doing pure math, and I thought, if only I was just doing algebra. And then, so then I did my master's in just algebra, and then I thought, if only I was just doing category theory. That would be great. And then I started my PhD, and I thought, category theory is great. If only I was only doing higher dimensional category theory. And then finally, I found my home, and that was where I had wanted to be all along. And actually, category theory is something that I think you can study much earlier than that. And I have been teaching it to art students at the School of the Art Institute. Not at the same level of rigor that one would teach it to graduate students, but still the ideas of it are clear and compelling and more relevant than solving a quadratic equation. Because let's be honest, how many times do we need to solve quadratic equations in our normal daily life? Not that many times. And even if we did, we could probably ask a computer to do it these days. You can probably just say to Google, what's the solution to this quadratic equation? And it will tell you. And as I like to say, when I was in middle school, our teachers used to say to us, you know, you won't always have a calculator with you. And now we just all have them on our phones. So yes, I always have a calculator with me. And I like to think I can preserve my precious brain power and save it for the things that my phone can't do. And that is category theory. So first, I'm going to play you one of my favorite pieces of Bach, which my phone can sort of do because it can play a recording, but it can't interpret it in this way. There is tons of math in Bach. There's so much math in Bach, I could speak for maybe 3 weeks continuously about that, so I won't do that. But this is from the 48 Preludes and Fugues. Bach wrote 48 Preludes and Fugues. He got very excited because a new tuning system was invented that meant every key was usable. Before that, only a few keys sounded great and the other keys sounded terrible. And then they invented a new system involving some mathematics so that every key sounded great. So Bach wrote a Prelude and Fugue in every key. There are 12 keys on the piano. There's major and minor, so that makes 24 keys. Then he got really excited and did it all again, so that makes 48. And this is from the second book. It's the Prelude in G minor, so first I'm going to play it for you. Thank you. So this piece is written in polyphony, which is how Bach wrote a lot of music. And polyphony means that there are different individual lines of music that are kind of independent of each other, and they wind their way around each other. And in theory, you could get 4 people to sing this, because each line of music is like a line by itself. So the top line goes, and the bass line just starts off like this and then goes like this, and then there's a second line that goes. When I first studied this piece of music, I got very confused by it, and I felt that I couldn't follow where the lines of music were. So I decided to draw a picture of it, and the picture came out like this. This picture is a very, very extreme abstraction of the piece of music, where I have forgotten almost everything about it except where each line of music is in relation to the others at any given moment. And abstraction is all about forgetting details, and forgetting details is kind of nice sometimes. And one of the things that happens is you get to see the abstract structure inside the situation. Another thing that happens is that you start seeing lots of different situations turn into the same thing if you forget some of the details. And that's what math is really about. It's about making lots of different situations become the same at some level. And that's really how numbers came into being. You kind of go, well, if I have one monkey and another monkey, that makes two monkeys. And if I have one chair and another chair, that makes two chairs. And if I have one table and another table, that makes two tables. Something's going on. If I have one thing and another thing, that makes two things. And it doesn't matter what those things are. So why don't I make an abstraction and go 1 add 1 is 2. And that makes all those situations the same, and I can put the details back in afterwards. So that's what abstraction does. And I think we forget sometimes that numbers are already an abstraction that we've all got really good at. And a lot of people say to me that they were okay with math until the numbers became letters. But that's just another level of abstraction. And these levels of abstraction, every time there is one to leap up, someone falls off. And that's when we teachers have to try and help everyone up those levels. Anyway, this is an abstraction. And showing this abstract structure helped me understand why I didn't understand. And you know how understanding why you don't understand something is the first step towards understanding it. So it helped me see why I lost track of the voices, because they cross over each other and they don't come back again. So this top one, the black one, is the soprano line, as it were, and it creeps its way down and ends up as the tenor. And the bass creeps up and ends up as the alto, and the alto ends up as the bass, and the tenor ends up as the soprano. That makes it a bit difficult for 4 people to sing. I know one person who can sing soprano, alto, tenor, and bass, but it's a bit unusual. So once I had made this structure, I really think it helps me play the piece better. Now, you don't have to know that the structure is there. You don't have to see this picture in order to listen to the piece. But I think that it helps me play it better. And I think this is true about mathematical structures all over the place. You don't have to know they're there in order to use the things that they're controlling. If we forget the paint and the light fixtures and the carpet and the chairs in this room will look a lot like other rooms. And we don't have to know where the structural walls are in this building to use the building. It's a good thing that somebody knows where the structural walls are. And this is what I think about math as well, that you don't have to know it's there. But if you do know it's there, then it helps you to use the situation or whatever it is, use it better. It helps you to fix it if it goes wrong. It helps you to maybe invent your own things and improve on the situation and develop something of your own. And isn't it nicer to develop something of your own than just have to use other people's things all the time? So people say to me, oh, I get by perfectly fine without math. And I say, well, maybe, but I get by better. So the funny thing about this picture is that I made this picture just before I started doing my PhD. And then when I did start doing my PhD, pictures just like this appeared in one of the first research papers I read. And I went, wow, I didn't know that was going to happen. It was a kind of do-do-do-do-do-do moment. And these are called braids in mathematics because they look a bit like braids. And mathematicians study them to see what happens if you move the strings around. Can you turn one braid into another by shifting it around? What happens if you look at it the other way up? Can you undo it without moving the ends? And this is also related to juggling. Now, I'm not very good at juggling. I used to just say, oh, I can't juggle. And then someone said to me, you know, that's what people say about math. And I thought, oh, yeah, that's true, isn't it? And I thought, yeah, but I really can't juggle. And then I went home in secret. And I juggled at home when no one was looking. And it was really odd, because once I had changed my mindset about juggling, I could juggle. It was really strange. I can't explain it yet. I'm still not really good enough at juggling to do it in front of an audience. So is there someone who would like to do a juggling demonstration? Yay! A big round of applause. What's your name?
I'm Grace.
Grace, wonderful. Here's the juggling ball. Yay! Amazing. Now, would you be able to walk across the room while you do it?
Ooh, I can try.
Yeah. Just try to imagine that we have a long exposure camera. So we're going to take a long exposure photo of Grace juggling so that each ball is going to trace a path out through the air. Can you imagine what that picture will look like? Would you do it again? Come this way.
Yeah.
would look like this. And here's one that I made with some illuminated juggling balls and a dark room and a long exposure picture. This wasn't me juggling. When I did it, it came out very wonky. So this was an 8-year-old boy who in the school where I did this. Here is one that I made digitally. So you can see, now if I do the world's most hilarious juggling demonstration, so I've got the green and the red ones in my right hand. The green one goes across like this, and while it's going, the blue one goes across, and I walk forward. And then as the blue one's going across, this is a really good demonstration, as the blue one's going across, the red one goes across this way. And because they're going under each other and I'm walking this way, they get completely looped up. And if I turn it this way, you see it's the same as the braid in my hair. And this is a braid, another braid that mathematicians study as braids. And one of the things they study is things like how looped up are they. This one is very looped up. I tried to make the Bach braid in my hair one time. It didn't go very well. As you can see, you would need a band here and here and here and here pretty much to hold it together. Whereas a normal braid, one of the clever things about it is that you only need one braid, one band at the end. If I take this out and then pretend I'm in a shampoo commercial, which I sort of always wanted to be when I was little. Oh, my necklace is now tangled with the microphone. There we are. Then you can see that this one is significantly more tangled than this one. This one, the green strand, is pretty much floating free, and so is the black one. And then if you just ignore the green and the black ones for a second, you see that the red and the blue ones are tangled with each other as a separate issue from the green and the black ones. But that means that you could move this one all the way over here, move that one all the way over here. This is the kind of thing that mathematicians study. It's part of the field of topology, where you think about when things are kind of the same as each other if you wave them around a bit. Mathematicians study them because it's fun. And actually, a lot of math we study just because we're curious about it, without a particular application in mind. And sometimes the applications appear later. And this might be related to early diagnosis of Alzheimer's, because some people think that might be because of the brain cells getting tangled up. Then the mutation means they're tangled in the wrong way. So you want a way to see whether this tangled up brain cell is actually different from this tangled up brain cell, or if it's just been waved around a bit and you're looking at it from a different angle. And to see if that's true, you can't just stick your finger into someone's brain, take a brain cell out and wave it around. So then you need some more abstract way of studying it, and that's where the math comes in. Anyway, because I couldn't braid my hair like this, I made it into a pie instead. This is my Bach pie. It's banana and chocolate, so it's a Bach pie. So now I'm going to talk about something that looks more mathematical, which is factors of 30. Maybe we can remember what the factors of 30 are. They are 1 and 2, 3, 5, 6, 10, 15, and 30. Very good. That's not very interesting. So it's a bunch of numbers in a straight line. And we sometimes end up writing things in straight lines just because we live in a three-dimensional world. So we write on two-dimensional pieces of paper in one-dimensional straight lines. And a lot of our math we have forced into one dimension when it had natural geometry the way it was already. And some of the complication just comes from that squashing into one dimension. And I also say this is why I don't like tidying up the papers on my desk, because they had a natural geometry. I don't want to force them into one dimension. Anyway, we can find the natural geometry of this situation by seeing also which numbers here are factors of each other. And then we can draw a kind of family tree showing which ones came from which ones, and we can have 30 as the kind of great-grandparent at the top. And then 6, 10, and 15 go into 30 with nothing in between. And then 5 goes into 10 and 15. 2 goes into 6 and 10. 3 goes into 6 and 15, and 1 goes into 2, 3, and 5. And so now we see it's a cube, which I think is much more interesting than a bunch of numbers in a straight line. And it's a cube an interesting way up, because usually we think of cubes sitting flat on one side, but this is a cube standing on one corner. And it's related to the kind of brain teaser that says if you suspend a cube from one corner and you put half of it in water, exactly half of the volume underwater, then what shape does it make on the surface of the water? And the answer is a hexagon. Because, and you can see from this picture that there will be these 4 vertices beneath the level of the water, these 4 vertices above the level of the water, and then if you look carefully how many sides it goes around the front and around the back, it's 6 there. So it's a hexagon. Now we can also relate it back to braids again, because if I make this an actual cube, and then I can wrap it up with ribbon, I can see where the ribbons go. And I'm going to make up a rule for myself saying that the ribbon coming in from the right is going to go on top. Now, math is actually more about making up rules than we usually say to people in middle school, because usually when you're first learning math, everyone tells you the rules and you have to follow them. And that's much less fun than making up your own rules, especially if no one ever tells you where the rules came from. And actually those rules are all there for a reason. Whereas I know that in actual school, there are often rules that are kind of arbitrary and you can't tell why they're there, and then you get really annoyed because you don't want to follow this rule. Most rules, I like to think, in a sensible society, rules are there with sensible reasons and that it's all about living in harmony with one another and not doing bad things to each other. That's my optimistic belief in the world, anyway. And so in mathematics, it should be the case that the rules come from somewhere, but you can also just make rules up and see what happens. Like if you invent a new game, you make up the rules, and then you see what kind of game you produce. And I say to my students, they're all art students, so they don't like following rules that much either. But I say to them, you can make up any rules you want as long as you follow them, and if your rules cause a logical contradiction, then your whole world implodes. But that's okay, you just then start again and make a new world. So here, my ribbon coming in from the right is going to be on top, so then I'm going to follow the sides down here with the same color of ribbon. And then here I need a new color of ribbon, so this one's going to be green. It comes across from the right. On this side, I'm going to start the colors of ribbon in the same places, so it's going to be blue here, red here, and green here. But because the shape is different, it's going to follow the faces around in this way. And then I hope you can see that if you shuffle the red and the blue crossing down here and move the green ribbon up there, then this braid becomes that braid. So mathematically, we would say those are the same braid, because we just looked at it from a different angle, or you could shuffle them around and produce one from the other. And this is something quite profound in both topology and in higher algebra, because this string crossing thing is called the third Reidemeister move. Mathematicians love giving things fancy names. It makes us feel clever. And it's one of the 3 moves that you can use to show which tangled up things are the same as other tangled up things. You can reduce it down to a very small number of possible moves that create all the other moves, and this is the third one. The cube face pattern is called the Yang-Baxter equation. That's also a fancy name. But anyway, it's about wrapping presents up. And then I thought to myself, I saw this during my PhD as well. And then later I thought, hey, wait, what if I do that to my Bach braid? Because here I started with a cube and I wrapped it up and I got this braid. What if I start with a braid? Can I reverse engineer a present that's the exact right shape to be wrapped up by that braid? So here is that braid again. And I stared at it. And so what I want is one square face where every crossing is, so that the ribbon will cross over. So there's one square face here, a square face here. And do you know, it's a cube. And when I first realized it was a cube, I did exactly what I do whenever I prove an actual mathematical theorem. So first I go, oh my God, that's amazing. And then I go, oh, I'm probably wrong. And then 2 seconds later, I go, I expect everyone in the whole world knows this apart from me. And then 2 seconds after that, I go, it's probably trivial. So I texted a friend of mine, actually the one who can sing soprano, alto, tenor, and bass. And I told him about it, and he got really excited. He said, I think it shows that Bach was communing with the spirit of the Platonic solids. And I don't think that's what it is. And I don't know what it is. I don't know why this makes a cube. I've checked it several times. I built the wonkiest cube ever because I was in such a hurry to see if it was true. I ripped up pieces of paper. I stuck it together. I drew this thing on. It really makes a cube. I checked it wasn't trivial. I thought maybe every braid makes a cube. Well, no, it has to have 6 faces. Then I thought maybe every braid with 6 crossings makes a cube. Well, no, because you could just go take 2 strands, go cross, 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 cross. So I don't know why it's true. I don't know that it's useful, except that it's kind of cool. And I think that's enough sometimes. And if we expect everything to be useful, then, well, we can be waiting a really long time sometimes. The Platonic solids themselves date back 2,000 years. And it was only 2,000 years later that the first icosahedron was found naturally occurring in life because they made microscopes powerful enough to see viruses. And many viruses have an icosahedron shaped. But there was 2,000 years in between figuring out that icosahedrons are a thing and finding an icosahedron. So if you wait for if you're waiting for a useful use, you could be waiting a really long time. Together with, there's this other thing I think about saying math is useful, which is, when did any young person ever get interested in something because it's useful? It's like saying to someone, I'd like you to meet my friend. They're very useful. Whereas if we show what's interesting about it, well, that's more interesting. I think so anyway. So now we get to cake. And one of the reasons I love cake and making dessert is my favorite thing to cook is because it is nutritionally useless. All it's there to do is make me happy, which is great. And Battenberg cake is one of my favorite kinds of cake. It's quite an English cake. It is allegedly based on the crest of the Battenbergs. That may be apocryphal. But the main point is that you have two colors of cake, and you don't want the same color to touch the same color, because that would be terrible. But it's actually a mathematical structure as well. So we can make a little multiplication table of 1 and -1. So here we're going to put 1 times 1, which is 1 usually. And here we are going to put 1 times -1, which is -1. And here we're going to put -1 times -1, which is 1. So it's a Battenberg cake. And we can also do this. We can do addition of even and odd numbers. So if we add an even number to an even number, we get even. If we add an even number to an odd number, we get an odd number. And if we add an odd number to an odd number, even. And so it's a Battenberg cake. And we can also do this by multiplying real and imaginary numbers. Now, even if you don't know what real and imaginary numbers are, I'm telling you they're a Battenberg cake. And imaginary numbers are that thing that happens where they tell you in school, you can't take the square root of a negative number. And then the next year they say, oh, now we're going to take the square root of a negative number. So they're what you get when you take square roots of negative numbers. A real number times a real number is real. A real number times an imaginary number, imaginary. And if it's going to be a Battenberg cake, then an imaginary number times an imaginary number must be real. And it is, in fact, a Battenberg cake. And yes, I do this with my students, and I give them one that's not a Battenberg cake to see if they're paying attention. So if you do multiplication of even and odd numbers, then it's not a Battenberg cake. So not everything is a Battenberg cake. Well, let's look at this now, bed flipping, and do something similar. Bed flipping is why I've given everyone a little piece of paper with A, B, C, and D, and that's a bed. And mattress flipping is what we're supposed to do every season to stop our fat bottom from kind of pressing down in one part of the mattress the entire year. I never do it because I'm much too lazy. And actually, you know, a lot of mathematics comes from mathematicians being lazy, because you don't want to do the same thing over and over again. So instead of doing the same thing over and over again, you make a theory of that thing that does it for you, and then you let the theory do it. And I like to think of it as front-loading your effort. So it's more effort making the theory, but then the theory takes care of everything. So I think it's very important to be lazy in the right kind of way. There are various things we can do with our mattress. So, of course, if you were going to flip your mattress, you would write A, B, C, and D on it to remember where you are. And there's an aside here that I'd like to point out about supposed real-life math problems. There's an issue, I think, with making up very contrived real-life math problems and trying to make it like that's why we should study math, because I don't think we're fooling anybody. And my friends sometimes send me their children's math homework for hilarity. And my favorite one so far has been, you have 1 meter of string. You use 35 centimeters of it to tie up Eddie. And you use 30% of it to tie up Joe. How much do you have left to tie up Emma? And aside from why we're considering tying people up, 35 centimeters is not very long piece of string to tie someone up with. So this is a problem with real-life math problems. But here, very real life, I like this because we're going to make a multiplication table of the different moves we can do. So here, we're going to put 0 followed by 0, which is what you do if you're me and you're too lazy ever to flip your mattress. So all you ever do is stay in the A position. Rotation is what I'm calling rotation around this way. So if you do nothing and then do rotation, you land in the B position. Here you do nothing and then you flip over sideways. That's the C position. And here is where you do nothing and then you flop. That's what I'm calling flop, this way. So you end up in the D position. Now going down here, you do the move first and you do nothing afterwards, which is the same because it doesn't really matter when you do nothing. I like doing nothing all the time, basically. So this is going to be A, B, C, D down here. So let's try doing a rotation followed by a rotation. We start in the A position, we rotate, and then we rotate again. And that takes us to A. Here, we do a flip and then a flip. So we flip over sideways, and then we flip over sideways again. Also A. And here we flop twice. So start in the A position, we flop, and then we flop again. Also A. So what that tells us is that if we do the same move every season, we will never achieve all the possible positions. So we have to mix our moves up a bit. So let's try a rotation and then a flip. So we do a rotation and then flip sideways. We get to D. And we can try doing a rotation and then a flop. So start in the A position again. We do a rotation and then a flop. C. And here we do a flip and then a rotation. So start at A, flip, and then rotate. D. And then here, which is the entire point, I get to say flip, flop. So you go flip, flop, B. And then maybe you start seeing a pattern. So what do you think goes here? C. And what do you think goes here? B. And if we're good mathematicians, then we should actually check that it really does that rather than going, oh, I've spotted a pattern and be done with it. It does do that. But the real question is, how many Battenberg cakes can you see? So there's 2 here. There's 2 more there. There's 1 in the middle. The one I really like is the big one, where the whole thing is a Battenberg cake, each of whose small cakes was already a Battenberg cake. I call that the iterated Battenberg cake. Here I've put the letters in so you can see what they are. I've iterated the process of Battenbergification. That's what I've done. So the process of Battenbergification is like painting by numbers. All you have to do is decide which things are going to go in positions 1 and 2. So I could say it's yellow and pink. I could say it's chocolate and more chocolate. That's always a good thing. I could do a bunny and another kind of bunny. So now I've Battenbergified a bunny. Or I could do one kind of cake, Battenberg cake, and another kind of Battenberg cake, and that makes an iterated Battenberg cake. And mathematicians love iterating things. We're a bit like small children who just like doing the same thing over and over again once you've done it. So if we've got something we can iterate, then why not iterate it? So, but we can also represent this in an even more abstract way. Because once you've decided you're doing Battenbergification, all I had to do was tell you what I'm putting in positions 1 and 2. So I might as well represent it like this. And 1 and 2 can be yellow and pink. It can be light brown and dark brown. It can be bunny 1 and bunny 2. Or it can be cake 1 and cake 2. But what is cake 1? Well, cake 1 was just one of those things. And cake 2 is one of these things. So now I might as well take this whole cake 1 diagram and put it in the 1 position, and put this whole cake 2 thing and put it in the 2 position. And now this is the very extreme abstraction of the iterated Battenberg cake, where each of these branching points is telling me that I'm doing Battenbergification here and here, and then I'm Battenbergifying the results of that Battenbergification. And these are called trees in mathematics, and they're studied as mathematical objects. They're called trees because they look a bit like trees. They have a root and branches and leaves. Mathematicians get into very strange arguments about which way up the trees should be. And some people are convinced they should be the other way up, because obviously trees start in the sky and grow downwards. I don't know. But the great thing about an abstract tree is that it doesn't matter which way up it is, because it's telling us a relationship between things, rather than a physical object. And so now one of the powerful things about it is we can read it whichever way up we want. If you really want it to be upside down, you could always stand on your head. But we can read it downwards, which means we're taking some things and sticking them together. But we can also read it upwards and think of taking something and splitting it apart. And that duality is very useful to mathematicians. And I'm going to look at the sticking things together aspect, because we can represent all sorts of things by sticking them together. Here's a diagram of sticking 3 things together, where I stick the 2 on the left together first and the 1 on the right afterwards. And here is another one where I do it the other way around. So for example, I can ask if they're equal if I do 4 add 4 first, which is 8, and then I can add 2 afterwards, which is 10. And usually, because we're unfortunately writing in a one-dimensional straight line, we have to use parentheses to say what we've done, instead of having this nice picture in 2 dimensions. So this way around, it says add the 4 and the 2 first, which is 6. And then I can add the 4 afterwards, which is also 10. And I have to put the parentheses on the other side. And this we know as the associative rule for addition. But really, so we know they're equal. It's really about moving a little branch across on a tree. We just had to squash it into this slightly boring one-dimensional thing. And it's even more boring when you have more layers of it and you have a whole pile of parentheses all piling up on each other. Now, this is all very well, but this isn't always true. Math isn't just about studying numbers. And when you study things that are more subtle than numbers, then this thing becomes more subtle. So for example, if you study egg yolks and sugar, if you mix egg yolks and sugar together and then you mix it with milk and you heat it up, you get custard. If you do it the other way around, that says mix the sugar and the milk together and then mix the egg yolks with it, and in that case, you do not get custard. So these things are not equal. Whereas if you're making a cake, then the usual recipe for making a cake says cream the butter, the sugar and the butter, then beat in the eggs and finally fold in the flour and bake it. That makes cake. But it turns out, especially if you have a blender or electric whisk or something, then you can just basically chuck everything in the bowl at the same time and go wah. And it doesn't really make a lot of difference. But you might want to study different ways of putting it together. And so here is the one little move of moving one branch of the tree across from left to right. Here are all the possible ways of combining those ingredients where you're only adding one thing at a time. And each of these arrows represents moving one branch of the tree across from left to right. So this one is where I'm moving this little bee butter branch across from left to right. Here, I'm moving this branch, and I'm taking its little baby sub-branch with it. And then I'm moving the little baby sub-branch across to there. Whereas this way around, I'm going the other way. This shows all the different ways of making the cake. I took all these cake ingredients to one of my classes with art students once, and we tried it. And we discovered that if you mix butter and eggs together first, it looks really disgusting. But then if you beat hard enough, then in the end, everything kind of comes out all right. And this one's interesting because you need 2 bowls. Because you mix the sugar and the butter in one bowl, and you mix the eggs and the flour in a different bowl, and then you mix the results together afterwards. If you're really lazy like me, you don't want an extra bowl to wash up, so that's bad. But we discovered that all the cake mix turned out looking more or less the same-ish. Now, we didn't have ovens because we're an art school, but I did go and visit the Culinary Institute of America outside New York, and we did this, and they do have ovens. And we had an amazing lecture theatre kitchen with a kitchen at the front and ovens and cameras facing down, so that I've always wanted to be on a cooking show, so this was really fun. And we actually baked it at the end. And what happened was that it all turned out like cake. It's just that some of it rose more than others. So this one was really kind of flat. But it turned out, I think it was, the bottom one was also flat. But this one, and this one actually turned out looking all the same. It was just slightly difficult along the way. Because here as well, you have to mix eggs and flour together. That's also a very strange thing to do. But if you're only eating the cake at the end, then maybe you don't care so much whether it was difficult along the way. If you have an electric whisk, maybe you don't care. Maybe you like slightly denser cake. And it's interesting here because all the results turn out like cake. Whereas with the custard, it really isn't custard at the end. It's completely different. And when we're studying more interesting objects in math, there are different ways in which things can be sort of the same or not. And you get to make choices about whether things are going to count as the same or not. Just like when you're 2 and someone offers you a piece of chocolate cake, you know which piece of chocolate cake is definitely the best one. And if they don't give you that one and they give you that one instead, you'll cry. Whereas when you become an adult, you kind of become more relaxed about the fact that they're all more or less the same, maybe. And then with the cake, maybe you care if it's difficult to make. Maybe you care that your cake mix goes through a phase where it looks like vomit before you finish making it. Or maybe you don't. It's up to you. And we get to make more of these choices when we're doing higher mathematics than when you're doing middle school mathematics and you don't really get to make any choices. So you don't have any ownership over what you're doing. You don't feel like you have any input into it. This is actually a piece of very high-level mathematics that you wouldn't usually see unless you were probably doing a PhD, maybe in either topology or category theory or something related. It's called the MacLane pentagon, and it's all about how you combine things in different orders. I definitely didn't see this until I was doing my PhD. But it's really just about making cake, so I say, why not show it to everyone? And then one obvious question to generalize it, and mathematicians love only dwelling on one answer for a second and then immediately asking a broader question, was, well, what if I want to make chocolate cake? Because obviously I do want to make chocolate cake, in which case I have one more ingredient. And that means that all of my trees are going to have an extra branch on them. So they're going to be 5 branches, and there are a lot more trees with 5 branches on it. And if you draw all of those, then you discover that there are various of these pentagons sitting inside the structure. And if you stick them all together, you get this, which someone 3D printed for me. So in my book, there's a flat cut-out diagram that you can cut out, maybe not the actual book, or maybe the actual book, and stick it together. And someone made me this. They made me another one which had a nice hook so that I could hang it on my Christmas tree in the festive color of black. I somehow lost that one somewhere. I think it's because someone else wanted it on their Christmas tree, so they took it. So I've just got this one. And it's gone up a dimension. These are called the associahedra, and they're something quite advanced in topology. But every time you add another ingredient, you gain a dimension. So if you wanted to make something with one more ingredient, it's going to be 4-dimensional. That's a little bit harder to make. 4D printers aren't as advanced as 3D printers at the moment. And so this is one aspect of higher dimensional category theory, which is my field of research, which is really about making chocolate cake. And so in conclusion, if mathematics is the logical study of how logical things work, I like to say that category theory is the mathematics of mathematics. So it studies mathematics in the way that mathematics studies the rest of the world. It makes analogies between different parts of mathematics to try and make a theory so that you don't have to do the same thing over and over again inside of mathematics. And if I unravel that, then it says that if category theory is the mathematics of mathematics, then it is the logical study of how logical things work, which you may think is very looped up on itself, and it kind of is. But I like that. And I'm not trying to say that everything can be studied logically. So I'm not trying to say that category theory can do the whole of mathematics, and I'm not trying to say that mathematics can study the whole of the world either. But I think it's important to understand which parts of the world can be understood logically and which parts can't be understood logically. I think it's important to exercise the logical parts of our brain as a kind of core of our brain thinking. So that just like our physical core, which it's good to exercise, it's good to exercise a core so that you get more access to the rest of your power. If you have a strong physical core, it enables you better to engage the rest of your muscles from a strong core. And I believe that mathematical thinking is a strong core of the brain so that we can then access other parts of thinking, even though math isn't actually everything. There's a lot of life that isn't mathematical. But for me, personally, I think the most interesting parts are the interface between the logical and the non-logical. Not necessarily the actually illogical, but the parts we can't explain. When I play a piece of music, I love analyzing its mathematical structure and trying to understand why it moves me and why it makes me cry. And I'll get to a certain point with the explanation, and then I won't be able to go any further. There'll just be something at the end. I can say, oh, it's because there are so many fantastic suspensions, and suspensions make me cry. But why do suspensions make me cry? That I don't know. And that, to me, is where the beauty is, that exact point where the part I can explain logically meets the part I can't explain logically. And I have this image of the logical part of the world being a kind of sphere at the center of everything that we understand and everything that's in the world. And the aim is to put as many things in there as possible, knowing that we'll never get the whole universe into it. But as we get more things into the logical part, the sphere of logical things grows. And as it does, the surface area grows. And that surface area is the interface between the logical and the non-logical. And so I think the more logical things we understand, the more access we have to the beautiful interface between those two things. Thank you very much.
Any questions for our speaker?
So I'm math and music double major, and I'm curious if you can speak more about what it's like on like a daily basis to balance both the music side and the mathematical side of your brain, and what that's like for you.
That's a really interesting question, and I love the fact that you are a math and music double major, because people who aren't often say to me, oh, is it true that math and music are related? And often they say it like they're the first person ever to have thought of it. But it's a great question, especially because I used to be really more of a full-time mathematician. I started out as a kind of normal math professor. I don't think I'm particularly normal, but I was just being a normal math professor, and then I realized that I didn't think I was making the best use of all my abilities. And I believe very strongly that it's important to figure out what you're good at and what's unique about you, and then use that to contribute to the world in the best possible way. And I didn't think that I was using all my abilities to contribute to the world in the best possible way. And that's why I moved to Chicago, quit my tenured job, which is quite an unusual thing to do, and spent more time on doing outreach work, popularization of math, and more music, which I feel is important as another form of communication. And to me, it's a kind of balancing out of different things. There are aspects that are related, and there are aspects that are not. Bach is very mathematical to me, whereas other kinds of music are not. If I go to a Wagner opera, I love Wagner, but if I go to, I won't be able to do math for 3 days if I go to Wagner opera, because it completely messes up my brain. And I love analyzing the structure of music, and it helps me understand it. I recently performed the last Schubert sonata, and the process of studying it really seriously, more and more mathematical structure came out, which made it easier to understand, because I think that math, one of the things about it is it's an organizing principle, and it enables you to understand large things in small chunks because it packages them up. So I was able to understand the Schubert sonata in a much more easily digestible way for my brain, because I was analyzing it somewhat mathematically. It is an interesting balance. I often feel like it's like when you do an exercise at the gym and you have to stretch in the opposite direction to recover from that thing. So I often feel that practicing the piano stretches my brain in the opposite way from math, that kind of relaxes me by the opposite extreme. So I don't spend a lot of time just, although I joke about doing nothing, I don't actually spend a lot of time just watching television or something. I tend to relax from one thing by doing something else. And if it's not that, then I'll go into the kitchen and bake something, because I find that very relaxing. And one of the things I love about practicing the piano and also baking is that when I practice the piano, I get better. And I can actually see a direct link between the amount of time I spend practicing and the getting better. Whereas when you do mathematical research, unfortunately, you can spend years and not make any progress whatsoever. And so it's nice to have something else where I know I will make progress if I spend more time. And so that's another aspect that balances it out. Finding time is always an interesting thing. And so my piano life has definitely shifted, because there are certain types of pieces that simply require hours of practice every day to remain fit enough. And it's a bit like the fact that if you stop doing research, sometimes I'm doing something else, or when I was teaching full-time, you get into the middle of the semester and you simply have no time to do research. And then you go back to your research, you have no idea what you were thinking. And so you lose maybe a month by stopping for a week. And it's a bit like that. It's a bit like training for sport, I imagine, although I've never trained for a sport. But with piano, you get to a certain level of fitness, and then if you stop, you lose so much, and then it's a big effort to get back into it. So it's another thing where it's better to do it the whole time. So I try to do that with my research as well, even a little bit every day, just so that I don't completely lose track of what I'm doing. And sometimes I think of it like a jigsaw puzzle in my brain, where imagine you're doing a 10,000-piece physical jigsaw puzzle, but every time you leave the room, someone messes it up. And I feel a bit like that with math, that you're holding all these things in your brain, and when it's in the process of research, you can't write it down yet, because you haven't even understood it enough to write it down. And then every time you interact with a human being, it's a kind of dangerous moment where these pieces in your brain might move. And I think this is why it can be quite difficult to do research and interact with human beings at the same time. And it's one of the things, honestly, that makes teaching math difficult, because you may be trying to think mathematically and interact with humans at the same time, which is a challenge. So I don't know if I entirely addressed the question, but those are some of my thoughts around fitting those things in. Thank you.
Other questions?
Yes.
Just be loud.
Okay, so I care about cakes. So I was wondering if there was a certain permutation of the way things are ordered when you made the trees. So have you tried like different permutations and goodies, like if you mix the butter with the flour?
That's a great question, and that's a different structure. So I wasn't permuting the ingredients on the way in, because these are called associahedra, which means I'm only thinking about how they are associated together. There's another structure called the permutahedra, where you also have the possibility of permuting the ingredients, and that makes for a much more complicated structure. And I encourage you to draw all those trees and see how they're related yourself. It's an interesting structure.
Yes. You talked at the beginning about your passion for educational reform. In your ideal world, how would children be taught mathematics?
Oh, tiny question. I think one of the big problems, is that elementary school teachers are mostly still required to teach everything. And many of my art students tell me that the point they got put off math was the point where it got hard enough that you might need someone who understands math well to explain it, but you don't have specialist math teachers yet. And so round about 3rd or 4th grade, already there are things that general teachers might not feel comfortable explaining. And those of us who've taught math, we've probably all had the experience of teaching something that's a little bit close to the boundary of our own knowledge, and it's a bit scary. And once you become confident, if you're a generally confident mathematician, then you get to a point where it's fine. If someone asks you something you don't know, then you say, I don't know, that's a great question. Let's figure out how we could find out the answer. But if you're not confident, then that's when you aren't able to explain where those axioms come from. You know, I wonder how many elementary school math teachers can explain where the associativity law for addition comes from, and where the commutativity of multiplication comes from, or why the order of operations is the order that it is. And so at that point, when the explanations aren't there, it starts putting people off and becomes less like an interesting game or an interesting craft project, which is how it still quite often is in kindergarten and 1st grade, and then it becomes something where you have a bunch of rules flying at you, and it's the first place where you can be wrong, and no one really likes being wrong. Whereas in other subjects, you can't just be wrong. Like if you write a story, your story isn't going to be wrong. It might be less good and more good and things like that, but it's not just going to be wrong. And so I believe that there's a way of teaching math where there's less right and wrong, and plus we, together with the fact that it would be great to have specialist math teachers earlier. And I know that there are, I've talked to many school districts where they're trying to do that, and there are various things in the way. Sometimes it's the parents, actually. Sometimes the parents don't want specialist math teachers earlier because they worry that the teachers won't know their child, and they think that their child should have one teacher for everything because otherwise, you know, something. I'm not quite sure what. And often the teachers would really prefer that as well. Another thing is that I don't think we value teachers enough, and that therefore people who are good at math would not be encouraged to become elementary school teachers. And when I've been helping with elementary school math since I was a PhD student, and honestly people say to me, don't you think that's a waste of your abilities? And why is that a waste? I think it's the most important thing that you can do, especially early on when children come into school and they've all come from different backgrounds, and some children are already so disadvantaged by the family life that they've had. up to that point. If they arrive at the age of 5 and they're already disadvantaged, they need help. Otherwise, especially with something like math that is somewhat cumulative, they're just going to be behind forever and they're never going to catch up. So I think that's the point where it's most important. There are more specialist high school math teachers who have math degrees, but it's more likely that someone with a math degree will go in at that level if they're going to be teachers rather than at an earlier level. So I think in my ideal world, we would value teachers more, encourage more people who are good at math to teach math at an earlier level by saying, no, it's not a waste of your abilities. It's one of the most important uses of your abilities that we have. I would have more emphasis on projects which have no right and wrong. So I do projects with my art students which are, I've discovered that there's a pedagogical term for this, which I can't quite say it with a straight face yet, but I do think it's a great term. It's low floor, high ceiling. So there's a low point of entry. Everyone can get somewhere, but then there's no limit to really what the project can produce. So everyone can explore, and there isn't any particular answer that is being aimed for. It's just, let's explore this situation. And we can try and cram more math down people's throats. Some people say it would be terrible to graduate high school without being able to solve simultaneous equations. And the thing is that what ends up happening is that some people get dragged kicking and screaming, and they can solve simultaneous equations when they graduate high school, and then they will immediately forget it as fast as possible because they hate it so much. So what's the point of getting people to be able to do something when they're 17 and hate it so much that they never want to do it again? I think it'd be much better to preserve the curiosity and love of learning, even if there's less actual content knowledge at that point, so that people aren't put off. And sometimes I think that the way things are at the moment, we'd almost be better off if we taught nothing, because then at least we wouldn't be putting people off. And I've heard the unfortunately apt term, the bulimia model of education, where the aim is to stuff as much in as possible and then kind of vomit it all out as fast as possible. And I think that in my ideal world, we would move away from that. Of course, without the kind of testing that we have at the moment, we still need a way to somehow gauge how everyone was doing. But if we have teachers we trust and who are good teachers, then the teachers can gauge how everyone's progressing. We don't need tests to do it. We can trust teachers to do it. So that, in a large nutshell, is some aspects of my ideal world of math education.
Well, so on that note, let's thank the speaker again.